Okay, section 8.9, convergence of Taylor series. Basically, this section is going to ask the question, does a Taylor series actually converge to the function we're trying to estimate or not? And how would we go about knowing that? And then it's going to give us a way of calculating, or at least estimating, the error term. The first little box in the section, theorem 22, gives this now well-known equation. This is a polynomial for the first n terms of a Taylor series, and that's up until this point right here. And we realize that this thing is centered at A and is of order n. We look over here though and see this is a little bit new. What's going on here? Well, this looks very similar to this, but you'll notice that one thing that's happened differently is that instead of an A term here, we have a C term. And basically, if you read up on this, what you find out is that C is a value that's going to be between A and X. Okay? It's somewhere between A and X, and it could be that X is less than A, or X is greater than A, but whatever, it's going to be intermediate between these two. And if we plug C into this last little bit of this equation here, this gives us the remainder. It gives us what's left over after we've added all these initial terms and makes it exactly equal to the function. Okay? That would be swell if we knew what C was. But in general, we don't know that C is there. But using the mean value theorem, we know that there is a C that would satisfy this. So if we're asking the question, does the Taylor theorem converge to f of x, we would need to know that we had a continuous function that was differentiable over this interval, and at least differentiable up to the nth term, or I guess the nth plus 1 term. And it would be nice if it was infinitely differentiable. And that this last term here goes to 0 as n goes to infinity. Okay? So at the limit, this term right here goes to 0. That means that the preceding polynomial here, Taylor polynomial, estimates perfectly our function. Okay, so those conditions need to be satisfied. So one of the things that we'll be looking at in examples in this chapter are, does this thing, this last term, this remainder, as it's called, does that go to 0 as n goes to infinity? Alright, to give you a flavor of how some of these problems are solved, let me do example 1, or at least part of example 1. And what they're going to do is use the Maclaurin series to estimate e to the x. Okay, so we're familiar with that. Our e to the x is going to be equal to a Taylor polynomial, and we'll make it 1 plus x squared over 2 factorial plus x to the nth over n factorial. There's our terms of our Taylor polynomial, and then we have a remainder of, they say x, I suppose we could say that in a way, you know, we're going to have to plug in c, right, to get this. And we can say that this r value here, they call it r of x, and I'll maintain their notation, is equal to e of c. That's that magical value that's going to exactly fill in the remaining amount for e to the x after the polynomial's done, of n plus 1 factorial or x n plus 1. Now, I told you we don't know what e to the c is. Let's just pick one case where we've got a situation where x is greater than 0. Okay, therefore we know that here's 0 where we're centered at. There's x. C has to be intermediate in between here. So we know that e to the x is greater than e to the c. You can go through the example and look at other cases, but this is an easy case to illustrate my point. There's nothing surprising about the other situations. And therefore, we could say, well, that r of x is less than e to the x over n plus 1 factorial x to the n plus 1, like this, and then say, well, okay, now we could actually plug in x here and then look at our limit as n goes to infinity. Well, we already know what that is, because this is just x raised to the power divided by n factorial, or n plus 1 factorial. So we know that this part right here is necessarily going to 0, no matter what this is. No matter how big x is, this is going to 0, and it's going to cart along this finite number to 0. So this whole thing goes to 0, classic sort of limit idea, and therefore our remainder goes to 0. Therefore, if we pick enough terms in this polynomial, we can get any degree of accuracy we want to for estimating e to the x. And basically, that is how it's done. The next step is to actually try to estimate what is the magnitude of the remainder. And we're going to use a similar approach where we kind of fudge and estimate, well, about how big might this remainder be, to give us a kind of rule of thumb or a ballpark of how far off we are on our Taylor estimation.